along to another lesson with me, Mr. Wong. Today we're going to be looking at a physics concept known as work, kinetic energy, and potential energy. We're going to try and look at how these three components link with each other. Before we start, we need to complete a do now question. So it says a heavy roller is used on a cricket pitch between innings. It is moved with a constant force at an angle of so. In this diagram we see here, and we roll it for 28 meters. So what is the work that we've done whilst rolling this roller? Okay, we can think about it. Work is given as the parallel force to the object's displacement. If we look at the question here, the parallel force is this component here. This is the direction of the force applied onto the roller. Okay, we have an angle. And if we imagine this to be a right angle triangle, the force vector here and the parallel force here, to find the relationship, the parallel force is essentially F cos theta. So we just need to find the components of what theta is. We know from the question theta is going to be 30 degrees. And we know that the F parallel is just going to be S or F cos theta. Okay? F is 4,500, so that's 4,500. We know that our displacement is going to be 28 meters. So if I substitute that into my formula that I've written down here, I get this. So force is there, displacement there, and the angle there. If I plug it into my calculator, I'll find that the total work done is the following value here. And if I put it into three significant figures, I get 1099 or 109000 joules. The units for work is joules, but we can also use Newton meters. Just remember, another definition for work done is the change in kinetic energy. So that's the question here, and let's move on to the actual topic for today. In the previous lessons, we've talked about kinetic energy, we've talked about gravitational potential energy, but we're going to try and link these two concepts back to work done. So that's the central goal of today, and then once we've gone on to that, we'll look into how gravitational potential and kinetic energy is a form of conservation of mechanical energy of moving objects. Textbook reference is down here. Just remember, we talked about this last lesson as well. Anything that's moving is caused by a force. So the reason why a stationary object starts moving is because there is a net unbalanced force pushing on it or pulling on it. If an object is moving, it has kinetic energy. Okay? But let's say if I was to lift a book up in the air and then dropped it. Right? So I'm storing gravitational potential energy, and when I release the book, the acceleration due to gravity will pull my object down. And so that's why energy and motion are backwards and forwards with each other. What we're going to try and show is how work and kinetic energy are related. Or let's see how we can derive a formula for kinetic energy using the formula for work done. Alright, so what we talked about last lesson was that for an object to experience work, it needs to firstly experience a displacement. So you have to move the object has to move positions, and the position the object moves must be in the same direction or in the same parallel direction as the force. this little double bar here represents parallel direction. If the object is moved at an angle, say the one we have here, where it's being dragged at an angle up, then we work out that this is still the direction. So there is a perpendicular component. This is our perpendicular component here, our perpendicular force. And we also have a parallel component of force here. And that's the bit we're going to look at. And we find that it's using the cos theta relationship. Alright, let's try and split this up and show how work done and change in kinetic energy are related to each other. So if I have a net unbalanced force, so if there's a net unbalanced force, an object will experience some form of work done upon it. So it's going to move. Okay? If you have a look closely here, kinetic energy refers to an object moving. So if I have an object that is initially stationary and all of a sudden it moves, let's say 5 meters, then it's experienced a change in kinetic energy. It's gone from 0 to 5. And so another way of saying W work done, we can say delta EK. Delta means the change. K is for kinetic energy. Okay, so the change in kinetic energy is the same thing as saying work being done on moving that object. So they are equal to each other. Now we know in the examples we've talked about, the object was originally stationary, so there is no initial kinetic energy. So the kinetic energy here is technically 0. So the change in kinetic energy for a stationary object ends up being the final kinetic energy it has anyways. So I can rewrite it like so. Okay? So I can just say if my object was originally stationary, then I can get rid of delta and I can just say the total kinetic energy of an object that was originally stationary and then began to move is given by this formula here. What I also know is if anything has a force, it has a mass, and it gets accelerated. So I can equate energy with an object's acceleration and mass. And so we have this here. So we say that kinetic energy can be affected by the mass of the object, the acceleration from 0 to whatever displacement it ends up achieving, and also the displacement. So these three factors will affect the amount of kinetic energy the object obtains. But that's not it. There's actually a couple more components we can add onto this equation for kinetic energy. So if we go back to kinematics, we know that acceleration is v minus u over t, final minus initial over time, and we know that the displacement can be written as so. So half bracket u plus v times t. The reason why we're using this formula here, if you think back when we started doing our diagrams, let's say an object has started with initial velocity of 1 and it went to a velocity of 5 at the end. So this is the final velocity, this is the initial, and essentially the velocity changed in this particular direction, time being this bit here. So we're saying that this little area here is the displacement we're looking at. Okay? So let's just substitute these two values in. So A will go into here and S will go into here. We get this equation. So we find that kinetic energy is equal to this. As you can see, we can actually do a couple of quick substitutions first. Firstly, we can get rid of T and T. Okay. The next bit is we can move the half over to M, and we can times the V minus U with U plus V. And we get this. So we move the 2 over here, and we had these two solved together, which gives us this equation here. Now we know, because the scenario we're talking about is an object that starts from 0, so if it starts from 0, it has no velocity at the beginning, so U is 0 in this case. So we can rewrite this as well, or we can expand it and we get this. So we get a nicely expanded equation. What we do know is if an object is originally stationary and then it begins to move, it will have some value for V, so its final velocity will have some kind of numerical value. But if something started at 0, originally stationary, then U is 0. Okay, so this whole bracket here, if an object started motionless, equals to 0. And so we find that the kinetic energy is given by this formula. Okay, so that's quite a journey we've made. So we said that the kinetic energy of an object, if it was originally stationary and then began to move, can be shown by this formula here, MAS, and we went from MAS all the way to half mv squared. And so that's the relationship we can see here. Work done is equal to the change in kinetic energy. The kinetic energy of an object in its entire journey is half mv squared, where E is kinetic energy measured in joules, m is the mass measured in kilograms, and velocity is measured in meters per second. Let's try some calculation questions and see how we can solve them. Okay, so question 1, it says Bill is driving his car. That car has a mass of 1,900 kilograms through a small town at 50 kilometers per hour. Okay, so we already know what the kinetic energy formula is, and we're just trying to calculate that. So we have mass and we have velocity. Now remember, velocity in physics needs to be given in meters per second. Okay, so to convert kilometers into meters per second, divide by 3.6. Substitute that into our equation here. So m will be 1,900, and then v squared will be this value here. So we have that. M there, v converted from kilometers into meters per second. And so we find that the overall kinetic energy is 18325. And if I just round it off to 3 significant figures, 183,000 joules, or you can write, as another alternative, 183 kilojoules too. Let's look at question 2. Question 2, we're looking at some form of acceleration. So it goes from 100 kilometers per hour, slows down to 80 kilometers per hour before turning a corner. Calculate the work done by the brakes to make this change. Okay, so let's again look at our formulas. So work done can also be exploring the change in kinetic energy. And the change in kinetic energy, we said, is half mv squared. This is the final velocity minus half mu squared. This is our initial velocity. Okay, so that's our equations there. We need to convert these values into meters per second. So V is equal to 80 over 3.6 and U is equal to 100 over 3.6. So there's the values we have here. We now need to substitute that in there. The last thing we need to do is the mass. So the mass is 2 tons. In physics, the SI units you need to use is kilograms. So times this by 1,000. And so there we go. So now we have kilograms, we have the velocities as well. So I now substitute that into my equation. So there's my equation there. Those are all the parts that I have found and all the conversions I've done. So my mass is 2,000, put that in. My final velocity is 22.2 and my initial is 27.8. What I'll end up finding is the work done is 288 or 288840. Okay, or we can simply say 289 kilojoules. Notice that we have a value of negative. Now remember, work done is a scalar quantity, so we should only have positive values. So that's why the end rounded result is also a positive number. Question B, it says, if it takes 50 meters for this deceleration to take place, calculate the average force applied. Okay, so the average force applied, we now know what the work done is. Okay, we found that in the question on the top. We know that work done is based off force, parallel force, or net force you want, times the displacement. Our displacement in this part is 50 meters, and the work done is about so. Okay, so 288,840. Substitute that in. One of the good practices of calculation in physics is always complete your substitutions first, and then you can rearrange the equation. So to make F the subject, divide both sides by 50. And I'll get the net force to be 5,780 newtons. So that's that. Moving on to our next calculations, this time with a little bit more similar, where we're trying to look at the velocities and all that. So the question says we need to calculate the speed of the car in kilometers per hour after 10 seconds. Okay, so I don't think I ended up doing kilometers per hour, but let's see what we did here. So if we look at the question, the mass m is 1400 kg. The work done is 9000 joules. So that was in kilojoules. I just need to convert that into joules. And we have some form of acceleration for 10 seconds. So time is about 10 seconds. Calculate the speed after 10 seconds. Okay, so Alright, so if we would read the question, our object or our car was initially stationary. So u is 0. And so calculate the speed. So what we're trying to find is v here. What is v? So let's substitute all the numbers that we have into the equation. Okay. So what we have is 900,000 joules times 1 over 1400 v squared. Obviously, if anything times 0 is going to end up at 0, so we can rewrite our equation like this. What we can do is get rid of the half, so we can times both sides by 2. And we can also divide the 1400 over. And so v squared is equal to this. To get rid of our square root both sides. And this is our value in meters per second. Okay? And so it rounds off to 35.9 meters per second. If we want to do what the answer was asking, which was to convert into kilometers per hour, you can simply times our value by 3.6, which I can give you a rough estimate, would be about 129 kilometers per hour. Alright, we're down to the last question for work done and kinetic energy. This question, we have the car model of 40 kg. It accelerates from rest to 200 meters per second. It has friction force 0.25, that's the numbers, and it takes 8 seconds for that acceleration to occur. These are all the questions related to it. Let's break it down one by one. Okay. First thing we need to look at is question A. We need to find the acceleration of the car. We know that acceleration is equal to the final velocity minus the initial velocity over time. Okay, we know that time is 8 seconds. We know that the initial velocity, which is at rest, would mean u is equal to 0 and that v is equal to 20. So if I substitute these numbers into my equation, I find that the acceleration is 2.5 meters per second squared. Question B, it says what's the force causing the acceleration? So this is the acceleration we have here. We know from Newton's second law, force is equal to mass times acceleration. Okay, so we already know what the acceleration is here. We know that the mass is 40 kilograms. So if I substitute these numbers into my calculator, I'll work it out as the force causing the acceleration as 100 newtons. Question C, this time we're asking for the total force acting on the car. So how is this question different from B? Well, think about it this way. Say if we have a car, really poorly drawn car, and it's going in this direction. What we calculated in question B, that's the F net. Okay, so the total net force we experienced. The reason why we have F net is because there is some kind of frictional force. And according to this question, the frictional acceleration is 0.25. So where did I get acceleration as 0.25 from? From this equation here. N kg minus 1. Now, we know that acceleration is meters per second squared. But if we look at the formula from Newton's second law, F over m, F is in newtons, so it's in newtons. M is kilograms, so that's where n kg to the power minus 1 comes from. So we have acceleration going this way, and that contributes to the overall net force, which means that the actual force, the total force on the car, so the force on our car, is actually a bit bigger than the overall net force. So it's a slightly bigger. Now, to account for that, what you can do is add on that acceleration value. So the total acceleration we calculated was 2.5, but this number is accounting for the acceleration we experienced because of the friction of the road. So if I add 0.25 onto this value, I'll find the total force acting on the car is 110 newtons. Question D, how far does the car travel? We can work it out using kinematics. So ut plus half at squared. Originally, because it is stationary, so u is 0. So it's just half 0.25 times 8 squared. Okay, we're using 2.5 as the acceleration because that's the actual acceleration the car was experiencing. And we find the overall displacement to be 80. Another way you can work this out is using the work done formula. So W equals to F times S. So just move F over under W and you should be able to work out something similar along those lines. And then E, what's the work done against friction? So we're trying to work out the amount of work done to overcome friction. And we know that the frictional force, the difference in frictional force, if we look at the two values here, is 10 newtons. Okay, so the overall acceleration or the overall force we experience on the car is 100. The total amount that's acting on the car is 110. So the frictional force, our frictional force contributes about 10 newtons to this. About 10 newtons. So if I substitute it in, S is 80 and F is 10, then the total work done is about 800 joules. If I want to look at the total work done by the force, so I'm looking at 110 because that's the total force used by the car. 110 times 80, and so the total work done by the force is actually 8,800 joules. And that's how you do this question here. Okay, so this is essentially what we came across. We first looked at work done as the displacement of an object when a parallel force is exerted on it. We looked at how to work it out if we were exerting that force at a particular angle. And last but not least, we found and proved that work done is the same thing as saying the change in kinetic energy. Now let's go through a little scenario here. One of these ads back in the day, speeding, no one thinks big of you. So people say speed kills. Let's actually prove that with some of these calculations. Let's say we have a car that is traveling at 60 kilometers an hour, and then we have another car that's traveling at 120 kilometers per hour. The mass of the car is the same. If we run through the calculations, the kinetic energy required to slow a 60 kilometer per hour car down is 2.09, 10 times the power of 5 joules. And if we double that speed to 120, the kinetic energy is now 8.32 times 10 to the power 5. So what you can see is all we essentially did was increase the velocity by 2. So if you increase velocity by 2, the work required, so the work required or the kinetic energy required to stop the car actually increases 4 times or 4 folds. Okay, and so that's why speed kills. It actually takes, if you double the speed that you're traveling, it actually takes 4 times the amount of energy to stop the car compared to when you were originally. So that's what we show here. And so that's basically what we find. And it shows exactly why when a car is speeding, is moving faster, it actually takes them longer to stop. And that's because work needs to be done, more work needs to be done to stop the car. And that's basically it for this part about work done and kinetic energy. Thanks for joining.